In this video, we will interpret the standard deviation. We will use Chebyshev's rule and the empirical rule to help us do this. With a mound-shaped symmetrical distribution, the mean, median, and mode of the data are all about the same value, and that's why we have the symmetrical shape. When we are interpreting the standard deviation using Chebyshev's rule, this is also called the at-least rule. Chebyshev's rule applies to any data set, regardless of the shape of the frequency distribution of the data. It is possible that very few of the measurements will actually fall into one standard deviation of the mean. So we say it is the at-least rule because at least 75% of the measurements should fall within 2 standard deviations of the mean. And at least 88.89% of the measurements will fall within about 3 standard deviations of the mean. Beyond 3 standard deviations, we have Chebyshev's inequality, which is 1 minus 1 over k squared of the measurements will fall within k standard deviations of the mean. So the letter k represents your z-score. If you're talking about 2 standard deviations within the mean, you could substitute 2 for the letter k. Now this is very useful when your z-score is not an integer, like 2, -2, 3, or -3. If you have a z-score of 1.5, you can simply substitute 1.5 for k into Chebyshev's inequality. And that will help you to determine what percentage of the data falls within that z-score from the mean. Our other rule is the empirical rule. The empirical rule is a rule of thumb that applies to a data set with frequency distributions that are mound-shaped and symmetrical. Here's an example of the mound-shaped symmetrical distribution curve. And I've also included what percent of the data falls within each of the standard deviations from the mean. So you can see that approximately 68% of the measurements fall within 1 standard deviation of the mean. So to fall within, that means you are considering to the left of the mean as well as to the right of the mean. So 34 and 34, that is about 68% of the data falls within 1 standard deviation, according to the empirical rule. So if we expand this to 2 standard deviations, approximately 95% of the measurements will fall within 2 standard deviations of the mean. So looking at our distribution curve, it's about 13 plus 34 plus 34 plus 13 and those decimals associated. So that would be about 95% of our data. And finally, within 3 standard deviations on each side of the mean, we have about 99.7%, that's almost all of the measurements, falling within 3 standard deviations of the mean. So the relation between range and standard deviation, we can discuss that next. The standard deviation should not be much larger than 1/4 of the range. The larger the data set, the greater the tendency for very large or very small measurements. These are the extreme values to appear. When they do, the range may exceed 6 standard deviations. So we have 2 different approximations for the standard deviation. When we take the range and divide by 6, that represents 3 standard deviations to the left and 3 standard deviations to the right of the mean. That makes a total of 6. So that gives us an approximation of the standard deviation within 3 standard deviations of x bar. That would be the mean for a sample. When we take the range and divide by 4, that represents 2 standard deviations to the left of the mean as well as 2 standard deviations to the right. That makes 4 total deviations. So that will approximate the standard deviation within 2 standard deviations of x bar, which is our sample mean. In our first example, we have an environmental study in Death Valley. How hot does it get in Death Valley? The following data are taken from a study conducted by the National Park System, of which Death Valley is a unit. The ground temperatures in degrees Fahrenheit were taken from May to November in the vicinity of Furnace Creek. So we have a table of values to use. These are in no particular order, but as you notice in the table, I'm going to put these values in numerical order from smallest to largest. So 142 was our smallest data value, and 182 is the largest measurement. In other words, 142 is the coolest temperature, which doesn't seem very cool at the Fahrenheit scale, and 182 is our hottest temperature on the Fahrenheit scale. So we have a table of all of our x values compiled. When we add those x values, that is the sum of x. 2,338 is the sum of the x values. When we square 2,338, we have 5,466,244. That is our squared sum. In our next column, that's reserved for the x squares. Remember from the previous video, we are taking our x value and squaring it. So in this case, 142 will be squared, and that equals 20,164. And then each measurement is found in the same way. The measurement is squared, and that makes our second column. Adding all of our x squares for the sum of x squared, we end up with 392,788. We will use this information to find sample variance and then our sample standard deviation. First calculation, x bar, is the mean of the data. Well, since we already have the sum of our data, we simply need to divide by the number of measurements, which is 14. So when we make this calculation, 168 is the mean for our data set. Our next calculation is the sample variance. So we're beginning with our sum of x squared values, subtracting the squared sum of our x's divided by n, which is 14, and all of that is divided by our n minus 1, which becomes 13. So this fraction becomes 390,446 when we divide. The numerator of our fraction results with 2,342 divided by 13, and you can see that goes on for a non-terminating decimal, so we'll make the approximation of 180.2 for our sample variance. Once we have the variance, we can take the square root of that value, and you notice I went back to using the decimal value to have a more accurate answer in the end, and our standard deviation is 13.4. The next thing we want to do is to count the number of measurements in each interval, that is, in each standard deviation from the mean. So x bar plus or minus 1s represents all of our measurements that fall between a z-score of -1 to +1, or all of our measurements that fall within one standard deviation from the mean. Next, we want to find all of our measurements within 2 standard deviations of the mean, that's x bar plus or minus 2s, and finally, all of our measurements within 3 standard deviations of the mean, and that is x bar plus or minus 3s. We have the data set written again, and just as a reminder, the standard deviation, 13.4, the mean is 167. So to be within 1 standard deviation of the mean, below the mean I am subtracting the standard deviation. Above the mean I'm adding 1 standard deviation. And these are the boundaries, if you will, for that first standard deviation. So looking back to our original data set, 9 out of our 14 measurements are within 1 standard deviation of the mean. 9 divided by 14 then gives us 0.643, and that result in percent form is 64.3% of our data falls within 1 standard deviation of the mean. Our next calculation, 2 times the standard deviation, or 2 times our 13.4, means we're either adding 26.8 or subtracting 26.8 from the mean. The results are 140.2 on the lower end, or 2 standard deviations to the left of the mean, and 193.8 would be 2 standard deviations to the right of the mean. So the measurements from our data set that fall within this range would be actually all of our measurements. So 14 divided by 14 equals 1, which is 100% of the measurements fall within 2 standard deviations of the mean. And then I think it would make sense for us to know already that we would expect 100% of our data to also fall within 3 standard deviations of the mean. But if we calculate it, 3 times the standard deviation results in 40.2. That's what we're either going to subtract from the mean or add to the mean to find those x values under the curve. And again, all of our data will fit in this range, which is 100% of our data. The next thing we're going to do is compare the percentages we found in Part B with the percentages given by the empirical rule and Chebyshev's rule, because we want to know what rule does our data follow. So within 1 standard deviation of the mean, our data says percent falls in that range. Compare that with 68% for the empirical rule and a low percentage possible for Chebyshev's rule. So basically anything greater than 0%. It could even be 0%. So it looks like falls short for the empirical rule. So it's looking like Chebyshev's rule so far. X bar plus or minus 2 standard deviations. 100% of our data falls in this area, and the empirical rule expects 95%. So we have at least met that percentage. Chebyshev's rule, 75%. So our data does follow with the empirical rule. Within the 3rd standard deviation, again, our data has 100% of the measurements falling in this range. Empirical rule expects almost all of the data, 99.7%. The last part is to calculate the range and use it to obtain a rough approximation for the standard deviation. So keep in mind the range is our largest measurement subtract the smallest measurement, which ends up being 40. Our standard deviation, remember, is 13.4. So that is the actual value. We want to compare that with the approximations we're about to make. Within 3 standard deviations, S is approximated to be the range divided by 6. So our range was 40 divided by 6, and that is 6.67. That's less than the actual standard deviation. Within 2 standard deviations, the standard deviation is approximated to be the range, which is 40 divided by 4. That result is exactly 10. That also is less than our actual value. So what might account for these approximations to be smaller than the actual standard deviation? Well, our approximations are less than the actual values, perhaps due to the fact that we do not have any extreme values. All of our data fell within 2 standard deviations of the mean.